about it in seventh period yesterday, and I do not think I did a great job explaining it. If any problem where there is a transition, where you're going from sliding to rolling, you've really got to be thinking about what's happening. And there's a lot of ways to mix this problem up and to make it more confusing. Let's do the most basic version of this problem possible, which is level ground, and the object is just sliding across the ground like a bowling ball on a slick surface, and eventually it begins to roll, and by the end it's rolling. Does that make sense? So and I don't remember enough about what the problem is asking about, but the crux is, no matter which shape we're talking about, the object begins on a slick surface so that there is no rotational motion. Now, don't take that as the way every one of these problems has to be. They can mix this all up into a number of different ways, and I'm afraid that it's really easy to become complacent that, well, it's always going to start this way and it's always going to end this way. No. There's a lot of ways to kind of add this problem in. So let's start at the beginning, where this portion of the surface has no coefficient of friction. The object has some velocity, which I'll call V naught, and every part of the system is traveling at V naught, and omega naught equals 0. So it is not rotating. Now, there's going to come the part of the system where there's friction. And during this part of the problem, there will be two things that occur. There's a transitional time. This is the point where the object is going to begin to slow down. So its velocity is changing. I would say that its velocity is some function with respect to time. Right? It is not a constant any longer. It is slowing down. So I want to be really clear too. I'm trying to be diplomatic. It's slowing down right now. It's getting to be slower. But the angular speed, which is also a function with respect to time, is speeding up. Right? It's beginning to have an angular speed. So it's starting to speed up its rotation while it's slowing down its linear velocity. It's a lot of words, and it's a lot to keep track of, but ultimately, if we decide that this direction is the positive direction, during this time, the acceleration is negative and the angular acceleration is positive. Those two things have to be true. That's the only way you can transition from not rolling to rolling, is to start speeding up the rotation while we slow down its motion. Eventually, they're going to sync up. And when they sync up, someplace over here, we're going to reach that instantaneous moment when the linear velocity is linked together with the angular velocity. That's the condition for rolling. And at that point, we'll have some V final and some omega final. So we'll put that has to be the condition. This is the process of going from sliding to rolling. Now, I want to get rid of this stuff down here because it's in the way. And let's state the obvious things, like there's a coefficient of kinetic friction and a coefficient of static friction in this section. And most of these problems ask for the same thing. They ask how far the object will travel until it's rolling. Although I drew it like that, I probably should be better and indicate that this process begins the moment it hits the rough patch. Sorry. See, the eraser's coming out. That wasn't my intention, but sorry. Now, there are, I think, 3 things you have to do here that I'm thinking of. And I'm not sure how students come up with this on their own. I think this is really something where you need somebody to kind of show you. You need to figure out what the accelerations are, because there are 2 of them. There's an angular acceleration and a linear acceleration. So that's the first 2 things that have to happen, is figure out what the linear acceleration is, what the angular acceleration is. But the third thing is to figure out how to use those. And I think that's the part that is tough. And that might be where, you need somebody else to kind of show you. I think finding the 2 accelerations for you guys should be relatively easy. And I know you might balk at that, but there's not that many forces acting in the system. And it's obvious where they're acting. So if you start considering the forces that are acting on the ball as it travels in this area, that part should be easy. And please do so. Draw in the arrows that represent the forces acting on the ball. I would draw them where they act on the ball. Pick one of your pictures and indicate all of the forces that are acting in the system. Do that on your own. And then I'll clue you in as to whether you were right or wrong. This part is easy. So if I draw them where they act, there's gravity downwards. At the point of contact, there's got to be a normal force upwards. Those 2 are balanced. So net force in the y direction has to equal 0. Normal force equals mg. It's on level surface. To me, that goes without saying, but there we go. Horizontally, there's frictional force. Has to be. It's acting here, and it's got to be this direction. And you should know what kind of frictional force this is. Did you put a K there or an S there? Which one is it? I can count on this class to say nothing. It's got to be K. It's got to be kinetic friction. It is sliding across the surface. This is kinetic friction. So net force in the x direction equals ma. Kinetic friction is negative. It equals ma. Be deliberate with direction or you'll have trouble. This one is causing a clear slowdown in the object. I drew this force negative. Anyways, be deliberate about direction. It's a big deal here because we have to make sure we have the things in place to help do what has to happen here. The acceleration has to be bringing the wheel to rest. That's what it's trying to do. It's trying to stop it. But at the same time, it's forcing it to roll. We're going to reach a point in a few minutes where there's going to be something I'm going to tell you that's going to be weird. We haven't gotten there yet. This is the easy stuff. Now, this portion, what I'm going to do right now, I don't think I have to prove. Negative mu k mg has to equal ma. I think it's all right there, and I think you guys should have no trouble doing any of that. And it embarrassed me a little bit that I know that it's probably not true. Like I probably should have to say, it's kinetic friction, so that equals mu times the normal force, and the normal force is right here, and sub it up, all that kind of garbage. I don't want to do any of that. The acceleration equals minus mu k times g. This is how much the wheel is accelerating, and it's negative. It is slowing it down. I'm expecting that nothing there is particularly new, and I should have expected you to be able to do it. But I note that was first semester, and although many of you got A's and B's, recall is tough. Now, the angular stuff is new. That's right now. But which of these forces, cause torques. Does the weight cause a torque? Again, I can count in this class to say nothing. Yes, ma'am. It depends on where I put the pivot point. Good observation. Where do you think the appropriate pivot point should be for this problem? Center of mass is actually the appropriate place for the pivot point in this problem. The system's not rotating yet. So as we start looking at the torques, if you don't have a given pivot point, you have to choose center of mass. That's going to come up in our next unit a lot. It's not going to come up as much right now, and it hasn't, where it felt like you could choose any place. But it's not pivoting about this point yet. That will only begin to happen once that point is no longer moving with respect to the surface. So right now, the pivot point has to be the center of mass. So once I choose the pivot point as the center of mass, does that help narrow down which forces are causing torques and which ones aren't? Can the weight cause a torque under these circumstances? No torque arm. Can the normal force cause a torque under these circumstances? Can't. The angle is 0 degrees. The only thing that can actually cause a torque is friction. Friction acts at the outer edge, so the torque arm is the radius, and clearly the angle is 90 degrees, and it's causing a positive torque. If you look carefully at the direction of the torque, even though it's into the board, we said that this is the positive direction. The positive direction for roll has to be this direction to correspond with what direction we called positive. This is where you, as problem solver, make decisions about what it means to be positive. We're looking for the conditions for rolling to occur, and these are still both vectors. So you need to find a consistent thing that is positive and stick with it. Into the board is positive for this problem when it comes to the rotation of the disk. That being said, a little low on space here, so I'm going to slide this to the side for just a minute. And we'll talk about, well, maybe not that far. We'll talk about net torque equals I alpha. And a reminder that torque is R dot F dot sine of the angle. In dealing with torque, there's just more parts. There's not a lot here, though. It is the frictional force that is causing this torque. It's acting at the outside edge of your ball or your wheel or your disc or whatever it is. So R mu K mg. It's still going to be R times the frictional force times the sine of 90 degrees. None of that's any different. And that has to equal I times alpha. And we are intentionally indicating this is a positive acceleration. It is causing a rotation in the direction that we want the system to roll, or that we expect the system to roll. Now, actually I should solve that for should solve that for alpha. So alpha equals R mu K mg over I. I'm going to kind of make this smaller. Right now, that represents what's happening to the right now, this is the conditions that the wheel is experiencing for its linear speed, right? Except that the acceleration is negative, so we could write this as everybody okay with that? And right now, this represents the angular speed of the wheel. It starts from rest and is increasing, so I could write this in terms of its angular speed, but put in now I know I left this in terms of I, and I didn't put in the moment of inertia of whatever shape they gave us. But you understand if we do this in terms of I, you can put all the shapes in and get the answers, right? So I'm going to kind of leave it like this. Here's the leap of logic that you need to take. And it was one that we had way back in like August. We reach the state of rolling when this equals this times the radius. That's when we reach the state of rolling. We can find out when that occurs. Maybe not where, but we can certainly find out when that occurs. Because this occurs at the same time that this must occur. So that's what we have to look for, is what time does this happen? Once we have the time, we can go back and figure out how far it slid. But we need to figure out the time it takes to slide to this point. Now, if you don't understand how to deal with this information, remember, these two things are related by R. Rolling occurs when that happens. This side is speeding up. This side is slowing down. We're looking for when they meet in the middle. So I'm just going to do this substitution. I'm going to put in V naught minus mu k gt equals, I know this is a mess, and just hang with it for a minute. It'll be okay. It would be prettier if we put in the moment of inertia, and I'm intentionally not. Okay, don't forget the T. I had to squeeze it in there. Now, I know this looks like a mess. Let's collect terms, shall we? We're looking for T. So we're going to collect terms, and it's going to be messy. So this is all algebra. Do you notice that when it's algebra, I get rid of everything else and just kind of work the algebra? So I'd encourage you to find ways to do that too. I look at your homework, and it's kind of funny the different ways you guys do this. Just especially if you're digital, waste the digital paper. What are you going to do, run out? If you guys are using regular paper, I'll give you paper. Spread your work out. It makes a difference on how well you do your algebra. Your algebra skills matter here. V naught equals, I'm going to distribute the R, and I'll get mu k g plus mu k m r squared g over I all times t. Done a lot of algebra in one step. You might take more. Now, I've made this intentionally more complicated than you would have to do so. And the reason is right here in the middle. You understand that this is just some fraction, right? Every version of I for something that rolls is something with mr squared in it. So this is the result of a half or 2/3 or 2/5. If you had put in the moment of inertia of the shape, this would look much prettier, wouldn't it? I left it out on purpose, not to make it more confusing, but to give you a little bit of I don't know, to make it seem like you could maybe think about it for just a little bit. Do you notice if I is bigger, it makes this term smaller? Think of the things that we have. I equals, right? There's mr squared, 1/2 mr squared, 2/5 mr squared, 2/3 mr squared. These are all the things that roll, right? And there's other ones, but this is most everything that rolls. A ring, a hoop, a ball, and a hollow ball. I is bigger in the denominator than you notice that that's going to make this portion of the fraction smaller. Do you see that? And if I is a smaller number, I have a smaller number in the denominator, it's going to make this whole thing bigger. It's kind of weird, but it sounds to me as if the object is harder to turn, it takes less time in order to get rolling. Well, that's what we have here. That's clearly what it says, isn't it? Now, if that's not true, you can figure it out. You can put in the two things. What are the two shapes in the problem? Pick one of these. I'll do one of them, and you do the rest. Do you want to do the hoop, or do you want to do the solid sphere? We'll put the hoop in. Okay. So we're going to put the hoop in. That means that V naught equals mu k g plus mu k mr squared g over mr squared times t. We need t. That's what we're going for. So I cancel out the mr squareds, and you'll notice I get mu kg plus mu kg. You guys all see that? So V naught equals 2 mu kg times t. So it takes this long to reach rolling. This is how long it takes to reach the condition for rolling. How far does it go? Pick your favorite motion equation. Doesn't matter which one you choose. Pick one that will solve for delta x. Based on what I have here, I'm probably going to do, I don't know, maybe delta x equals 1/2. No, I don't want that one because I don't know what the final velocity is. So I think I'm stuck with 1/2 at squared plus v naught times t. I think I'm stuck with that. Right? Because I don't know what the final velocity is. So, ready to go? Delta x equals 1/2 a. A was the acceleration. Negative mu k mg. No, there's no m in it. Just g. T squared. Eesh. V naught over 2 mu kg quantity squared. Plus, eek, V naught times t. This is a mess. V naught over 2 mu kg. It's icky, isn't it? It's all going to make sense. One would hope. I'm seeing that I have I have a mu kg and one of those in the denominator. I don't know, maybe I should do this slower because I want to make sure I don't lose somebody. So how about I go ahead and distribute and get 2 mu kg all squared plus eek, come on, v naught squared over 2 mu kg. I'm seeing that some stuff's going to cancel out, so I'm ready to do it. I'm going to do that and one of those, but just forget that that's a 4 now. And I have a 2 times that 4, so that makes it an 8. So if I do all the math, I get negative v naught squared over 8 mu kg plus v naught squared over 2 mu kg. I don't know. This seems like a lot of work, Mr. Shelton. 8 and 4. Subtract 1 from the 4 and get 3. And wow, boy, Mr. Shelton, did you really expect us to do this for homework? Well, you certainly don't want to do it on the test, do you? Do you have any idea if that's right or not? The top is meters squared per second squared. Mu k has no units, but g is meters per second squared. What's our unit? Are we supposed to be getting something in meters? It's not proof, but it certainly is evidence that it might be true. Now, I get that this was an algebra nightmare, right? The physics stuff wasn't so terrible, but look at all that algebra. And if you repeat this for the ball, which, by the way, you'd have to go back to here to repeat for the ball. The only thing that's going to change is going to be whatever this is. That number will be different. You're still going to get this. Think of the things that are likely to have controlled this. Do you think it will slide farther if it's going faster? Does that make sense that it's on the top? Yeah, I think so. Do you think it makes sense that if the surface is stickier, it'll start rolling sooner? I mean, I think that makes sense. There'd be more friction. It would make it turn faster, right? Also, slow it down sooner. So it makes sense that it's there. G's going to be there, right? Because if there was no G, there'd be no normal force. The whole reason that it's touching the surface is because gravity's pulling down on it. Those things being there makes sense. Getting to here, wow, that's a lot, isn't it? How many times in the 30-something years they've been giving the exam has this problem been on the exam? Twice. Never since the 90s. I'm not saying I think we're due. I don't. I don't think they'll put this question on the test in this way. You've got to understand why I thought it would be appropriate for us to look at it, though, right? I don't want your first time to be on the test. When they had this on the test the first time, they had a solid ball, 2/5 mr squared. They asked, in many steps, how far it slid until it started rolling. They asked many parts. They asked, what was the acceleration? That was a separate question. They asked, what was the angular acceleration? That was a separate question. They asked how long it took until it was rolling. That was a separate question. They asked, what were the conditions for it to be rolling? That was a separate question. They eventually asked, how far did it go until it was rolling? If you could do these parts, you got 8 out of 15 points. You understand that's a 3, right? Automatically, just this FRQ. 8 out of 15 points. Now, I agree, this is a lot, and it's a lot of time to waste. I'm not sure if you can do it or not, but I think I think it was appropriate for us to do it. So, we've done it. It is a very unlikely question on the AP exam.